have control of the computer again. And right there, slideshow, and current slide. Okay, all right. So the last thing we talked about briefly, we discussed the fact that 1011, that is a nibble, and that equates to our binary to a hexadecimal number, and we went through the table last time, right there. So that's, it looks like it's 1213, which is the letter C, right there. So that there is one hex digit, right there. A word is 2 bytes, right there. And most of the time we're going to be working in words. That's 8 bits, right there. So we're using an 8-bit microprocessor or microcontroller, so most of our data we're going to be talking about is going to be in words, right there. That's 2 hex digits. 2 hex digits, right there. Now, you will sometimes see the term double word, and you'll sometimes hear the term quad word. A double word is 32 bits. A quad word is 64 bits, right there. Most modern desktop microprocessors are 64-bit processors today. Many of the microcontrollers, in particular the ARMs, are going to be 32-bit. There aren't too many 16-bit microcontrollers. You know, just kind of throw out that. There are some. Texas Instruments puts out a couple. I can't remember who else puts out one. Silicon Labs doesn't. They put out only 8-bit and 32 bits, right there. And the reason is when you're getting to a 32-bit microcontroller, you're really getting into a system that is not quite big enough for a full-blown microprocessor, but a little bit too much for a standard microcontroller. The 8-bit microcontroller is still probably the #1 microcontroller out there if you don't count the ARMs that are in cell phones. That's there. You know, because most mobile devices are using some form of the ARM, and the ARM actually has 2 flavors. Has anybody ever heard of an ARM processor? You never read the tech sheets for, you know, don't read the geek magazines, I call them. You know, what's the one that they have in Malaysia? There's a version I can't remember. I read it from time to time. I used to read Byte magazine and PC World and Gadget World and all these where they do reviews on cell phones, right there, and tablets and things like that. When you look at the ARM processor, there's 2 flavors. One is the A processors. They're on the current, Apple is using the A9 processor. That's an ARM processor. And then there's the M family. The M family is our microcontrollers, and typically most ARM processors that are using microcontrollers are probably using the M4 family. That's there. The M4 is a microcontroller, or anything that, say, a Cortex-M anything. Cortex-M3-M4 is a microcontroller type device. Anything with a Cortex-A something is more of a microprocessor type device. So the ARM processor really has a microprocessor, you know, family, which is the A family, and then there's a microprocessor family or a microcontroller family, which is the M family. That's not going to be on the final exam, but just to kind of throw out there, when you hear the ARM, you'll hear M something. That's actually a microcontroller, and that's what you would see, for example, on like an Arduino board. That's an ARM processor. And it uses an M3, I think the Arduino board does. When you look at, say, for example, the Raspberry Pi, which is using like for an A8 processor. If you see the A, it's more of a general purpose microprocessor. You see an M, it's a microcontroller when you talk about ARMs. We're going to be talking strictly, this class, 90% of our discussion is going to be resting around microcontrollers using the 8051, but this course is titled Introduction to Microprocessors, so we're going to be talking about microprocessors as well. But they all use that term. So when we talk about microprocessors, you're going to see 16, 32, and 64. This course used to be taught on the 8086, which was a 16-bit microprocessor. Right there. So I talked a little bit about the difference between k-bytes and normal. This is a kilobyte is actually 1024 bytes. Right there. It's a little bit more than 1,000. When you see K in the digital world, it's not K as in the rest of the that there. And again, I know I'm repeating some of this right here. All right, let's get back into some of this. And I don't remember how much of this I covered. I've had kind of an interesting morning where things have kind of gone completely messed up out there. When we look at inside of a standard computer system, and this is true for any computer processor-based system, whether it's a microprocessor or a microcontroller or anything similar, we have certain units, certain parts to that there. The difference between a microprocessor and a microcontroller is where some of these are at. The CPU is a central processing unit right there. That actually is what does all the thinking. It moves all the data around. It does all the math, does all the logic functions. And that's also referred to sometimes as the ALU. Arithmetic logic unit right there. So you'll hear the term CPU. A lot of times people that are not computer type people will refer to the box on a desktop system as the CPU. That is not true. That's the computer system with the keyboard, the mouse, and the monitor connected to it. Those are input and output devices right there. But the memory, there's two types of memory in a computer. There's RAM and there's ROM. And if I'm repeating myself, it's because I don't remember where I stopped last time. And I sometimes repeat myself on purpose. That there, RAM is random access memory. This is typically temporary memory. That is memory that when you turn the computer off, it's gone. You're sitting there typing. You spent 6 hours working on this report, on this lab report to turn in. The power fluctuates. You've lost everything. It was all stored in RAM. It's gone. That there. So this is temporary memory. Data is lost when the computer's off. That there. The term random access is an incorrect term, in my opinion. That there. Random access means that I can access it directly by just applying the address on the address bus, and we'll talk about that, and reading that memory location. You can do the same thing with ROM. There used to be a type of memory called sequential access memory. And sequential access memory is basically a tape. It can be paper tape, it can be, and none of you are old enough to remember tape memory devices on computers. You might have seen the old movies where you got the big computer that's about 5 feet tall and it's got the two reels that go back and forth. Anybody ever see that on the movies? That there? That's sequential access memory. It's on a tape. And in order to find data on that memory, you have to fast forward or rewind the tape to a particular location. Not used today, fortunately. Right there. I've had computers in my early days when I was young that used tapes. One of the first computers, actually I wrote my final year project paper as an undergraduate on a BT-103, which was put out by a company by DEC, and it had little 2 cassette tapes that would forward back, and that was the disk drives. There was no disk drives, it was a tape drive. And it acted like a disk drive. It'll speed up, find the data, read the data, rewind, find the data, and read the data from the tape. That's it. I've had computers where I had to load in BASIC off of a cassette tape. That's there. So I've had tape-based computers before. Fortunately, I haven't seen them in about, I think the last one I saw was probably 32, 33 years ago. So it's been a while since I've had to play with tapes on a computer. That's there. So those are sequential access. Both ROM and RAM are random access. Even though one's called RAM, they're both random access. And they're addressed the exact same way The chips look very similar to each other. The only difference is that random access is set up in such a way that it requires power to store the data. Read-only memory, you can program the chip, take the power off, and the data stays in the chip. These are both chips. Now, what is not memory, and a lot of people will refer to as memory, is hard drives. And I include in this here flash, pen drives, SD cards. All these are referred to as storage. Right there. Storage and memory are different. They do the same thing. They have memory. They have data that you can store data on them. But when you look at ROM, that is a IC in the computer system that's part of the motherboard. If it's a desktop computer, it's within a chip if it's a microcontroller, but it's memory that is stored in the computer system. When we look at a desktop computer and we look at ROM, you find very little ROM in a desktop computer. Very, very little ROM in a desktop computer. That's there. And the reason is the only ROM you find in a desktop computer is what they call the BIOS, is enough information to tell it to go out and look for the operating system in storage. That's why I could take a desktop computer and I could put Windows 7 on it. I could put Windows 8 on it. I could put Windows XP on it if I want to go that old. That's there. I can put Windows 10 on it today. I can put Ubuntu Linux on it. I can put Fedora Linux on it. I can put all kinds of different operating systems in the same computer. That's there. So that's because the operating system is stored in storage, and then it's loaded into RAM when we boot the computer up. So desktop computers will go to the storage to get the operating system. Same thing with an Apple computer, a Mac. The difference is your choice of operating systems. It's iOS 10.8, 10.7, whatever version. I think 10.9 is about ready to come out. You can't run Linux or versions of Windows in a Macintosh without running something like Boot Camp or Parallels or VMware or some program that allows it to run both operating systems. Right there. You can, does anybody here own a Macintosh or Mac computer? No. Okay. They're a little expensive for the Malaysian market. That's there. Yeah, there. In the U.S., they're very popular among the rich kids. The normal students all have PCs, laptops. They have normal laptops, but the wealthier kids will go out and buy iMacs to show them off. They're a status computer. That's there. So, but if you have a Macintosh, whether it's an iMac desktop or whether it's and by the way, I don't have a Mac. I used to have one on my desktop where I worked simply because I hired somebody who later left, and I took his computer. I didn't buy it for myself. That's there. Well, that's what he gets for leaving. He doesn't get to take his computer with him. That's there. And since I was the chair, I kept it. That's the advantage of being the boss, right? You work twice as hard, but you can steal the computers from people that leave. But regardless, I could boot it up in Windows through a program called Boot Camp. That's there. But it had to boot up in some type of Macintosh environment first, and then it would run Windows as a program, and it would run Windows much slower than it would run, iOS. That there. Desktop computers such as you buy here the Dells, this one here is different. This is made by Microsoft, so obviously it's designed to run Windows. That's there. So it's a little bit like the iMac. That's there. But I've got a Fujitsu laptop, and my wife's got a Dell. Whatever. We could put whatever operating system on there that we want. We're not limited to Microsoft's operating systems. It just so happens that Microsoft's operating system is the most popular. It's probably not the best. That's just a comment there off the side, is that I don't think that Windows is the best operating system out there. I prefer versions of Linux, but the problem is that Linux, because not very popular. Most of the software is available for Windows-based machines. That's there. So, but those are stored all in storage and loaded into RAM right there. So when we look at desktop computers, we will find far more RAM and very little ROM. A typical desktop computer today is going to contain, if you go down to any of the computer stores, you know, I'm too lazy to go downtown, so I usually just go to, Wandsworth Walk. There's a number of computer stores there, and I buy a laptop at Wandsworth Walk or any of the computer stores that there, and I buy a laptop. It's probably going to come with anywhere between 4 and 8 gig of RAM, right? You know, if you go low cost, you might find some older used machines with 2 gig of RAM right there. But typically, most laptops are sitting with 4 gig. It's probably the most common, and the little bit higher end systems will have 8 gig of RAM right there. So that's what you've got. If we were to look at the amount of ROM in a desktop computer, you're probably talking less than 1 gig. Considerably less than 1 gig. You don't have much ROM in desktop computers. That's there. Now, when we get into microcontroller-based systems and embedded systems, that ratio flips. That's there. When we look at our 8051, we're going to see that it's got somewhere in the neighborhood of like 4 or 8K of ROM and like maybe 256 bytes of RAM. You know, so in other words, we don't have a lot of RAM in embedded systems right there. So we run into that particular ratio. For this slide, the takeaway is really RAM is temporary. You lose power, it's gone. ROM is read-only. You can't write to it on a general rule. That is also not true. So I'm spending a lot of time on this slide here. ROM used to be program it once and you throw it away if you want to erase it. You cannot erase ROM, nor back in the old days. That is not true today. Most systems have some type of upgrade or a firmware update where we can rewrite to the ROM. So, right there. So as we look at this system here, I know I went through this slide, so I'm repeating a lot here, but let me kind of go through here. Typically, we have the address bus, the data bus, and the control bus. Now, these here do not talk directly to the buses. What talks to the buses are their controllers, right there. So your computer monitor is going to have a graphics card in it. The graphics card talks to the address bus, the control bus, and the data bus. The monitor is connected to either a D connector for VGA. It's connected to a little square one for DVI, or now that you've got data port is out there. A lot of the video cards got HDMI output, so you have all kinds of graphics, standards out there. This has got a DVI or a, and this connector is not very reliable. This has it's got a data port output, so I have to use an adapter, which seems to be giving me trouble to get a VGA out right there. So, right there. Printers are usually tied to, and keyboards are usually tied to USB ports today, right there. Disk drives, if they're internal, they're tied to a serial ATA port. So there's a serial ATA controller that talks to the buses right there. If they're external, they're probably going to be USB of some type, right there. So actually, I'm just going to say these here don't talk directly to the CPU, but they go through some kind of intermediary circuit. They're indirectly tied to the buses through other devices, right there. So, but we're looking at 3 buses. A bus is a group of wires, right there. And again, we've gone through some of this, but I'm repeating this because a lot of these questions are going to show up on your final exam. So seeing them twice doesn't hurt you, right there. I'm just going a little quicker. The memory bus says what location in memory. If we look at memory as a big, long stretch there, this is memory location F231. This is F230. It's just a series of locations where data is stored, and each data location has an address, just like your house has an address, Just like your phone has an address, only you call it a telephone number. You know, if I call 017-223-1245, the switchboard at 017 is what, Maxis? The switchboard at Maxis will know which cell phone in their network to ring, right there. So when we put a particular memory address on our memory bus, that's going to tell our memory system which chip to look at and which location in that chip, right there. And we'll get into memory, that's there. The data is what we pass back and forth. That's there. And we can either pass 8 bits, 16 bits, or 32 bits, or 64 bits at a time. That's the width of our data bus. The processor we'll be using for the lab is 8 bits. An i3 processor, an i5 processor is going to be a 64-bit processor. That's there. And our control bus is the traffic cop, or traffic signals. It says which direction we want to move our data. What type of data is it going to be? Is it going to be memory we're talking to, or is it output we're going to be talking to? That's there. So we have those signals there. These are just, I'm going to skip through these relatively quickly. It just simply says that the larger the data bus, typically we can move more data. The higher end processors tend to have wider data buses. That's there. The bigger the data bus usually means that's going to be larger. Data buses are bidirectional. That is important as we look at some of our chips later on. And that's it. The number of address that there, this is an important formula right here. That tells us how much address space that a particular microprocessor can access. If we have a 24-bit address bus, that means you can address 2 to the 24th, or roughly 1 meg of data. That's what the 8086 had, right there. Our processor actually can't address any external memory to speak of because it's so small. But if we go to a bigger version of our processor, it's only got 16 address lines. So it can address 2 to the 16, which is roughly 64K of memory. That's as large a program as we can put in. Now, in the case of our processor, that's not 100% true. And we'll see when we get into different types of processor architectures. The data bus, address bus, is unidirectional. The only person that can talk to the address bus is the microprocessor. Nobody else can do that. There are some exceptions. They're not going to be covered in this class, but there are devices that, for very high-end systems, they call them direct memory access spaces, and they're used, for example, if I want to move a huge chunk of data from a storage device like a disk drive into memory, and I want to do it very, very fast and bypass the microprocessor. That's there. Or I've got some graphics that I want to use, and I want to pull it from data from memory and send it to the monitor, and I don't want to go through the microprocessor. I can bypass the processor and use what they call directory memory access right there. We're not going to talk about that. We're not going to address those, but they do exist. So this is not 100% true, like a lot of statements you see in this book or any book when we talk about microprocessors. The reason is this book was written 10, 15 years ago. Lots of things have changed. Just like ROM, I mentioned that we have ROM devices that we can rewrite today. I have a motherboard that's 6 or 7 years old, and a new type of monitor comes out, or graphics card comes out, and the hardware is there, but the software in the motherboard's BIOS doesn't support that. They can issue a firmware update and update the ROM in the motherboard. That's there. And this is actually early. I'm starting to see a couple people doze off here. That's there. This is terrible here. I know this is boring stuff. That's there. Okay, and I'm not a good entertainer. I don't juggle. That's there. So okay, there. For the CPU to process it, that there, it has to be stored in primary memory. Primary memory is both ROM and RAM. That there. ROM provides permanent storage, fixed and permanent. Again, we just talked about that. That there. So Okay, now we're getting into new material. This I have not talked about. We have registers inside our microprocessor and microcontroller. Every processor and microcontroller is unique in the way that they set the registers. And the way we use our microprocessor or microcontroller depends a little bit on the register configuration, because that gives us what we have to work with in terms of places to put stuff, how we add, subtract, multiply, divide, move stuff around. So we set up the register set. That there. So when I first taught this class, I tried using the 8086 register set there as an introduction, but then we moved and started using the 8051, and they're so far different that people got very confused. So I'm only going to talk 8051 registers this semester. Right there. Just to keep life simple. Right there. But you have to remember that different processors have different register sets. Right there. And some have more registers, some have other registers. Some registers can be used for some functions and not other functions, and that gets really confusing. Is remembering that, and I forget those things all the time. Right there. Some ports are bit addressable, some are dibble addressable, some are only word addressable. And each processor changes. Registers can be 8, 16, 32, or 64 bits. Typically, they're the same size as the processor you're talking about, the data bus, but not always. An example is the 8088, for example, had an 8-bit data bus and 16-bit general purpose registers. Right there. The 8088 was an unusual processor, is that externally it was an 8-bit processor. Everything internally was 16 bits. And the reason why it existed that there is it was introduced back in the late 1970s. That there, all the processors up to that point were 8 or 16 or 8-bit processors, because the most recent one was the 8085. So the next one was going to be the 8086. It became a 16-bit processor. There weren't any chips to support 16-bit processors yet. All the memory devices were 8 bits. All the buffers, all the other I/O devices were all 8 bits. They couldn't sell them. They could not sell the 8086. So they came up with the 8088, which was the same processor internally, but it was 8 bits externally. They sold a bunch of them. A bunch of them. The reason is a small company out of the U.S. called IBM decided to make the first desktop computer using them. Well, it wasn't the first desktop computer, but it was the first desktop computer that IBM made. So the first IBM PC had an 8088 processor in it. So that became the first of the Microsoft family processor computers, was the 8088 in the IBM PC. Every other Intel processor for desktops is just a larger version of it. That's there. So that's why a lot of people still teach the 8086 and the 8088 is because the A7 is just a larger version. The original registers and everything that were in the 8086 are now available in the 88 or the i7, but then they're 16-bit versions. So that particular processor had 16-bit registers internally and 8-bit data bus. That's the only one that did that. Actually, the 188 did the same thing. Then they quit making. There was no 288. They strictly went to the 86, and then they went to the Pentium family. So, but generally, we're going to be using 8-bit registers, but we have a couple registers that are 16-bit registers. Right there. So when we look at a register, this is not our processor. This is processor ABC. We don't know what processor this is. But inside here, we've got the ALU right there. And now this is all within the CPU. So the ALU is actually part of the CPU. That there. I mentioned that some people will refer to that there. We have the program counter, and that's connected to the address bus. That keeps track of where we're at in our program. In our case, that's a 16-bit register. Get there? We have the instruction register that contains the next instruction that the processor is supposed to execute. Remember, the ALU is what processes the actual instructions. We have the instruction decoder, timing, and control. This actually takes the instruction and decodes it and tells the ALU what to do, right there. It also sets up the timing. There's various things that have to happen, and we'll look at it in more detail when we want to read, write to memory, or when we want to do that. So we've got this block here. And then we've got these internal registers, and these are just like pigeonholes where you store data temporarily, right there. And then on this side, we've got our flags. And normally our flags are also contained in another register called the program status word. The flags give us information like, was the last operation the result a negative? Was it 0? What happened right there? So in other words, you might see an instruction that says decrement and jump not 0. And I'm going to say A, comma, and we'll just say start loop right there. Right there. So what this instruction is actually doing is just taking A, which is a register right here, and it subtracts 1 from it and puts it back into A. If the result is not 0, then we're going to jump to this location. If it's 0, then we're going to go on and do the next instruction. And this happens to be a typical instruction we will see. But this uses the 0 flag inside our flags. That's an example of our flags right there. So as we go through here, this kind of gets into the ALU does the operations, points to the next instruction, interprets and affects it. We talked about that. So we get into this discussion here, and it seems like I've repeated some of this. I've taught this class so many times here recently, various versions of this, that I'm lost up there. So if I'm repeating, that's fine. I think I am repeating some of this up there, which doesn't hurt up there, because maybe you'll remember it if I say it twice. And I know that since I don't have notes that I'm reading from, that I'm doing it differently each time. It's not there. So regardless, we have what's called an opcode. This is B0 simply says that that's the instruction that we want to execute right there. Now, back when I started learning programming, we had a set of cards that said A, add A, B right there. That's an instruction that says A is going to be equal to whatever was an A plus B right there. The data goes this way, from right to left, right there. Now that instruction for an 8085 might be C2. That's the opcode. Now, fortunately, life has gotten good. We don't have to deal with opcodes. Life is good. We don't have to deal with opcodes. Back when I was learning the program, we didn't have an assembler. I was the assembler. So I would write my code out in assembly language, and then I would sit down and I would look up the opcode for every instruction, and I would write my code. My code would look like C23519. That would be what my program would look like. Would be a series of hex numbers. That there. So that's what the assembler does now for us. It takes our program and converts that to a series of hex numbers right there. So when you look at this right here, this is our memory location. These are our opcodes right there. Right there. This is actually our location in memory words up there. So again, the opcode happens to be whatever it is right here. Move 21 into register A. That register there is move into A the number 21 hex. That's what you would write. To move into A 21 hex. Remember, your data goes this way. Right there. Move into A 4 number sign 42 hex right there. Add a number 12 hex. These are the instructions that we would write today. Back in the old days, it would be E21, B0 42, 04 12, right there. So we would write these instructions. Actually, this is off here. They're off one. It should be B021, 04242, 0412, right there. So this is what the code would look like, right there. So again, this is the timing. I'm going to skip over that right there. Decodes that, sets it up, right there. And this goes through the steps right there. Now, we get into, and we're in good shape. I'm going to go through, since I'm duplicating, I'm probably going to go a little longer here. But there, our general purpose microprocessor contains nothing but the ALU, the registers, and the flags. In other words, it contains basically this right here. That's the generic CPU right there. It contains basically what you see right there. Right there. The microcontroller contains the microprocessor. So the entire microprocessor is within the microcontroller, but we also have a whole bunch of other things. The microprocessor is, for all intents and purposes, a single computer system on a single chip. It has everything that a desktop computer would have on one single chip. Right there. So, you know, there. When we talk about that there, now storage is another issue. It may or not have storage, but it would definitely have the interface to connect to storage right there. So everything you would find in a microcontroller, you will not find on the CPU. The CPU is just a subset. If we have a general purpose microprocessor, we typically have to have a complete system board for it. Now, you get into, or for example, the A processors, the A9 processor that's in the Apple iPhone, they're using the A9 core, and they're building what they call a system on a chip. And that's a different generation. We're not going to be talking about systems on a chip. A system on a chip is actually a custom design IC that contains the microprocessor and other things added, and they're typically made for a particular function. The processor that's in the iPhone 6, Apple designed for the iPhone 6. You can't go buy that processor off the shelf. It contains the A9 ARM core, but it contains a whole bunch of other stuff that Apple has added to it. It's not a general purpose microcontroller because you can't buy it off that there. It's a system on the chip, custom designed by Apple for that phone. And most cell phones, for size purposes, use custom designed chips out there. Okay, this is a block diagram. That there. This kind of gets into that there. So again, the microcontroller, the main thing when we look at it is that it's smaller, it's cheaper, and everything is on board. General purpose, you can make a full system out of that there. So embedded systems does one task or a series of related tasks, and that's it. I mentioned before things like a gasoline pump microcontroller will keep track of things such as the emergency push button, keeps track of how much gasoline you're pumping, may keep track of how much fuel is in the tank, it may keep track, but its purpose is to run that gasoline pump. You don't play video games on a gasoline pump. Now, I have seen some gasoline pumps that have video screens for playing commercials. That's here. I don't know if I've seen those here in Malaysia. In the U.S., they've become quite common. You know, you go to buy gasoline, and there's a little computer screen there trying to entice you to go into the store and buy candy or milk or whatever. And I know it's true here in Malaysia, but it's definitely true in the U.S. Most petrol stations make 90% of their money off the convenience store inside. That's where the profit's made. Off the petrol, that's a fixed price and there's very little profit made per liter of petrol you buy. So most of the profit is made off the candy bar that you can buy at Eon Big for 2 ringgits, you're selling for 4 ringgits at the petrol station, right? And I'm sure everyone has figured that out, right? you buy a bottle or a can of soda, Pepsi at the supermarket. It's what, 1 ringgit 50, something like that, and it's what 2 ringgits at the petrol station. So these petrol pumps will have commercials that will try to get you to go at there. And I'll be honest, if I'm driving from here to JB and I stop at a petrol station, I'm going to buy the overpriced stuff because that's there. So, all right. So, desktop computers do other things. Again, there's this family in between today that was non-existent that is the handheld mobile computing devices that are really, when I put mobile devices in this category here. My cell phone here is a computer system for all purposes. I can do word processing with it. I can surf the web with it. I can send messages with it. I can use a calculator with it. I can check exchange rates. I can check my bank balance. I can run all kinds of applications with it. It's a computer system that, by the way, one of its functions is it makes phone calls. Right there. I go back 20 years ago, and my first cell phone that I had was a little Nokia that did one thing and one thing only. And what was that? Made phone calls, right? That's there. Oh, and you could send text messages, I think, on the early phones. That's there. Now they call that a feature phone. I always called them the dumb phone, but I guess the marketing people didn't like the, if this is a smartphone, then that's got to be a dumb phone, right? That's there. So those really come under the category of mobile computing devices. They're not really a microprocessor because it's a customized C, and those are usually, they often refer to that as SoC, or system on a chip, right there. It's a customized C that's got that there. We won't be talking about that on the midterm or on the final exam. You won't that there, but it's a different category. And I don't know if I mentioned to this class, one of the things we run into when we talk about the microprocessor world or the digital world is that it changes faster than any other technology in the engineering field. If you're a civil engineer and you design bridges, the type of bridges you design today and the type of bridges that were designed 15, 20 years ago are very similar. You go to California, one of the most famous bridges in the world, and look at the Golden Gate Bridge here outside San Francisco, and you look at that bridge and its architecture, the way it's built today, and you go and look at the new bridge you're building at Penang, and you're going to find very similar designs. They're not going to be the same design because materials have changed, some of the design techniques, but it hasn't changed drastically. I look at, and the Golden Gate Bridge was built 150 years ago, and we're looking at a bridge today. The technology hasn't changed drastically. You look at this building, and this building is probably 20, 25 years old, as I look at it. UDKL is much up there, and this used to be just BMI, and then UDKL took it over. This building's about 20 years old, and you look at a new classroom built today, they're not that much different in terms of technology in the construction of the building. It's still basically a cement foundation with rebar in order to support the building. You're using stucco over brick for most of the walls. You do have out there, but the technology hasn't changed drastically in the civil engineering and the construction field. You look at mechanical engineering, and you look at engines today. What is the number one change in an automobile engine today over the one 30 years ago? Number one change. The electronics. That is the number one change. If you take away the microcontroller that controls the fuel injection, controls the timing, the engine itself is basically the same engine. It's a cylinder that goes up and down, or a piston that goes up and down in a cylinder. The piston compresses the fuel And the oxygen or the air, when it reaches a certain point, a spark plug will ignite the mixture. That will cause an explosion, which will push the piston out, which will then turn the crankshaft and make the car go forward. Right there. You look at the transmission. If you look at the major change is the electronics that does the shifting, and you no longer have to push your foot down on a clutch and shift from one gear to the other. Those are pretty much done automatically today. If you look at motorcycles, there's a lot of the motorcycles. I happen to have made the foolish mistake of buying a Vespa in order to get around my neighborhood. That's there. I mean, I love the Vespa, but it's got a completely automatic microprocessor transmission. There is no gears on that there. I just turn the crank, it reaches a certain level, and it's continuous. The transmission continuously changes. You buy an older, more inexpensive one, you have to shift from first, second, third, fourth gear. So the change has been the electronics, not the transmission itself as that's designed. So when we look at this particular part of electronics, it has changed far more than any other field of engineering, far more. So if you go into the digital and the microprocessor world, be prepared to read constantly. Power distribution hasn't changed drastically, other than the addition of computerized control systems. Every other form of the electronics world, or electrical world, the change has been the introduction of microprocessors into that there. You look at communications, the changes, we've got digital communications today. Television has gone all digital. Anybody remember the old antenna that you put on your house and picked up TV signals, and you had the big CRT, the old analog TVs? Can you even buy those today? They're gone, right? That's there. And when you look at a modern TV, what you find is a system on a chip, a dedicated microprocessor that generates, it's all computerized, computer generated. So when we look at everything, the change has been the microprocessor. And microprocessors change weekly, not every year, but I read a number of the journals, and there's new designs, new technologies coming out on a weekly basis. No other field of engineering changes so fast. So if you go into this area, be prepared. It's a very fast changing. That's it. I joke about the fact that 30 years ago, this field was in its infancy, and we were programming from cards. If you go back 30 years ago and you look at an analog circuits course, you're still looking at 3-loop, 4-loop equations. You're still looking at doing just Jordan elimination in order to solve systems of equations. The difference is now you got computer programs like MATLAB and PSpice to do the simulations, but analog electronics has not changed in 30 years. My notes from when I took my circuit analysis course back in 1970 whatever, that there, my first circuits course, that there, are still valid today. I could take the old Boylsted book that I used back in the late 70s, and I could use that same book to teach circuits today. Matter of fact, I look at some of our faculty, I look at the choice of books, and some of those books are books that I use as a student. That there. You know, so that tells you, in the electrical engineering world, things haven't changed that much. Power factor correction. Have you covered power factor correction in any of your circuits? That hasn't changed. You've got an inductive load. You calculate the number of R's you need to add to that are capacitive in order to bring the power factor to unity. What's changed is that now you've got computer systems in power plants that will actively, on a minute-by-minute basis, calculate the amount of correction and add capacitor banks in and out as needed to keep the power factor change. So the power plants change because of the addition of the computer system. But the basic science has not changed. In computers, the science is still evolving. That's there. I remember as a young person something called Moore's Law. Everybody ever hear the term Moore's Law? Gordon Moore, the founder of Intel, made the statement back in 1968 that the number of transistors on a microprocessor will double every 2 years. He said that in 1968. It is still true today. They keep talking about Moore's Law, that it's going to eventually fall apart. But that means that we've got 2 billion transistors on a processor today. In 2 years from now, you're probably going to see 4 million. That's how fast microprocessors are speeding up and that there. So, getting back to our course here, I went on a side there. Microcontrollers, and again, this has been a repeat course simply because I walked in and I felt that I needed to do this, is when we look at embedded systems, this is a whole series of examples of them there I've talked about before, and as you know, they're everywhere. Embedded systems are everywhere. You find an embedded system in my little thing here. This has got a little tiny 8-bit microcontroller in it. It might be a PIC, it might be an 8051, I don't know what's in here. Up there. It sends an RF signal to my little device here that then has another microcontroller in it that tells the USB to advance my slides. My car, your trip computer, your engine control, your airbag, the instrumentation, security system, transmission control, cellular phone, keyless interest, all these things are up there. I've done some work in the past. I am not an automobile microelectronics engineer, but I have done some work, taught some courses that there. I know some people that work for companies such as General Motors and International Truck that there. So I've seen some of these computer systems they're putting in that there. The 8051 was designed to be put into a car. That was its purpose when it was designed. General Motors needed a microprocessor in order to meet emission standards. That's why the 8051 came around, was for the automobile and in particular the engine control. But then airbags started being required. Airbags, has anybody ever looked at an airbag or thought about airbags in a car? Are they required in Malaysia, airbags out there? An airbag is something that has to have a microcontroller and a sensor that knows when you have a crash in order to explode and blow the airbag out. An airbag's expensive. You go to replace an airbag in a car, it's 3,000-4,000 ringgits easily. There are people that will steal cars in the U.S. just for the steering wheel in order to get the airbag out. They're that expensive. So if an airbag controller misfires at the wrong time, if it doesn't while the car is parked, you still have a 4,000 ringgit repair to replace the airbag. But if you're going 60 miles an hour, 100 kilometers an hour down the highway, you hit a bad bump, and that airbag, is activated. Now you have a crash, and people get killed. So airbag controllers have to be very, very well designed and very, very failure-proof. If they don't explode when they're supposed to, people die in a crash. If they explode when they're not supposed to, they cause a crash. So airbags are a very serious design issue. Same thing with anti-lock brake systems. Now, anti-lock brake systems aren't as big a deal in Malaysia as they are in Minnesota and the U.S. Because Minnesota has one thing that Malaysia doesn't have, and that's ice. That there. You go to brake on ice, the wheels will lock up faster than you think of that there. And if that happens, you lose control of the car. Now, in Malaysia, I think it's going to be a long time before you find ice on any of your roads. Now, water, you might need some hydroplaning, but that's not near the problem as ice and snow. So anti-lock brake systems are much more important in four-season countries. That there. But these are all things. Our microwave ovens today. How many people have a microwave oven in your home? Not necessarily in your room in the hospital. That there. But I remember when microwave ovens came out. That there, and it was like they were like $1,000 and they were this big and that there. Now you can buy a microwave for what, 200, 300 ringgits, and they have them in every house. That there, and they're all microprocessor controlled. That's it. So again, many manufacturers of general-purpose microcontrollers have targeted their processor for the high end of the embedded market. This is not so much true anymore. There used to be a family of microprocessors that were geared toward the high-ended processor. I've used some of them. One of the early processors I used for a alcohol interlock system, I used a processor called the 8188EB. It was essentially an 8088 with some microcontroller functionality added to it. And I put that in there because the system was a fairly involved system because it had to measure the alcohol level in a person's breath. It had to control the ignition system of the car. It had to do all kinds of things So you'll see the term embedded processor and microcontroller used interchangeably. I'm about ready to wrap up. I noticed that we got one back here dozing off, one over here dozing off. You've dozed off a couple of times. None of you ever had to take a course with a Catholic nun as an instructor. They always walked over and just smacked you up the side of the head with a yardstick when you dozed off in class, or threw an eraser at you from the front of the room. I don't have a yardstick or an eraser to throw, so maybe a pencil out there. Uh-oh. Okay, well, I lost it there. So, again, this gets into the whole discussion of why we use most critical needs is to decrease power consumption in space, right there. High performance embedded systems integrates more functions in CPU, but lets you decide which ones that they're. We won't get into this discussion too much of doing these what I want to call it, these mixed processors. In other words, they're a microcontrol processor with some microcontroller functions added to them. That's there. The reason is that particular area of microprocessors has gone away with the addition of the system on a chip processors. Right there. Now, what's not talked about here in these slides, and I'm going to kind of wrap up with this, is that we also have a series of processors that I call specialized, right there, processors. And one of those would be for, say, digital cameras, right there. A digital camera has a very high-end microprocessor that's designed for image processing. And you'll hear companies such as Canon has one called Digit. In other words, they call that there. And these are custom-designed microprocessors that do signal processing or image processing, and they're designed for one particular type of function. The most common types of processors that fit in that category are going to be your camera processors, some of your video cameras, some of your cell phones fall under that, but these are custom designed processors for one particular So they're very, very common. I say in cameras you will see them out there. So, all right. I'm going to kind of hit there. These are the most common form of microcontrollers out there. We're going to be using this one. The Zilog Z8, I think, is now out of business. Microchip PIC is a very popular one with people. Matter of fact, I think a lot of the people in the technology programs use the PICs. I worked with we had a company near where I used to teach that used PICs for everything because they designed the controllers for HV systems, heating, ventilation, air conditioning up there, and they use PICs for that. They use PICs for thermostats. So a lot of things like the air conditioning systems, Carrier, which makes a lot of different brands of air conditioners, they use PICs and everything. So the PIC is a very popular one. The most popular are probably the Intel and the Zilog right there. So, right there. So we will keep track of this is where we ended, and today's lecture was really more of a repeat that's there because we were hitting the key thing. Now what we're going to be getting into as we get into our next set of slides is we're going to be getting into the 8051 in particular and the details on the 8051. it became there. And one of the things to keep in mind on the 8051 is that my first slide back here said that it's Intel's 8051. Intel does not make the 8051 anymore. So what is really coming in here is that the largest number of diversified multi-source that's there. So as we look at this list right here, we can see that there's a lot of companies that make different flavors of the 8051. Intel is the original one. They've dropped out of the market. They don't bother with that. It's too little money for a company as big as Intel to bother with. That's there. They make their money off of their i5, i3, i5 families. They make money off of motherboard chips. They make money off of routers. They make money off of the desktop computers. They're not that interested in the embedded market anymore. Atmel is a very popular one. I know some people here that use the Atmels. I've used Atmel before. The Atmels actually has a fab here in Malaysia, Penang. The Philips and Synetis and Siemens, those are popular with military suppliers. Dallas Semiconductor and Maxim, they're popular with a lot of that there. And the Silicon Labs is the one we'll be using right there. So as we look at this right here, we'll look at the 8051 in particular. So next Monday we're supposed to have a lab. We don't meet on Wednesday this week because we never meet on Wednesday, even though I kept trying to tell everybody last night that we meet on Wednesdays, right? At there. My university back in the U.S., where I taught, always had classes Monday, Wednesday, Friday for daytime classes, Monday, Wednesday for evening classes, and Tuesday, Thursday. I have never taught in 30 plus years a Monday, Tuesday class. That is one of the most unusual schedules I've ever seen. That's there. So that's why my brain could not register the fact that this class last night doesn't meet on Wednesday, because Monday classes always meet on Wednesday. They always meet on Wednesday. I've been programmed that way for 35 years, 40 years probably. See, I'm 59 next month. I started college. Probably close to 40 years I've been programmed with university courses are always Monday, Wednesday, Friday, Tuesday, Thursday. Sometimes Monday through Thursday if it's a 5-hour class in the evening, and Monday through Friday if it's a 5-hour class during the day. So, but never have I ever seen a Monday, Tuesday course in 40 years of being around the university system. So, pardon me for being so pig-headed or bull-headed or however you want to, whatever animal you want to talk about there. Bullhead's probably a better term here, in not absorbing the fact that you were trying to convince me that we didn't have a day off in this class. Right there. So, and coupled that with that is that my other class, which is the second half of this class, the microcontroller course, does meet Monday, Wednesday. That's there. So, and I had to cancel it yesterday morning because of Intra, and then I didn't realize when I canceled it that they also weren't going to meet Wednesday, so they get a whole week off. So that class, I have to go back and repeat the previous lecture. This class, I didn't really need to. So with that said, I'm going to, hopefully my mouse will work long enough to, and yeah, I thought I went long today, but actually by the time I found the classroom and got started and started recording, I started 15 minutes late, so the lecture turned out to be about the same length, right? Yeah, so yeah, my mouse is dead, so.